So now, armed with yet another giant set of timeouts to explain all of the background, let's do the calculations. I'm going to do the weak base calculation and the weak acid calculation. There they are. H plus is KaCa to the 1/2. OH minus is KbCb to the 1/2. What? That's it? Yeah, that's the calculation for a weak acid and a weak base. Compare these to the calculations for the strong. For the strong cases, it is the analytical concentration. But for the weak, you have to multiply it by this thing called a Ka value or a Kb value. You know what those are. Those are the equilibrium dissociation constants associated with the problem. I am going to derive these equations for you in just a moment. But before we go there, I'm going to work a few so you can see how simple they are to do. What is the pH of a 0.1 molar acetic acid solution? Ka is equal to 10 to the minus 5. What is the pH of a 0.1 molar ammonia solution? Kb is equal to 10 to the minus 5. There we go. Let's work our way through. Step one, let's find out what we have by getting rid of any spectator ions we see in these problems. So right here we got acetic acid. There's no spectator sitting there. Right here we've got ammonia. There's no spectator sitting there. So neither of these things have any spectator ions. They're both neutral species. Wait, they're both neutral species. Huh. Are they charged? No, that's neutral. That's neutral. Are they strong? No, that's not strong. That's not strong. So what is this? It can't be H plus and it can't be OH minus. So it's either HA, B, BH plus, or A minus. Well, it can't be BH plus or A minus because it's not charged. Neither is that one. Oh, this one's an acid. It ends in ic acid. So this isn't acetic acid. This is HA. And this one right here, ammonia, it's a neutral, but it's not an acid. It must be B. Notice the first thing I did in these problems was to convert them into my turf, into my collection of symbols. I know you don't want to, but trust me, do that. Get used to doing that. And then when the problems get hard, it's nice and simple. And now it's time to do the problem. It is a weak acid problem here because that's HA. That's a weak base problem because that's B. So let's do it. H plus is equal to Ka, which is 10 to the minus 5, times the concentration, which is 10 to the minus 1, to the square root, is equal to 10 to the minus 3. Down here, the OH minus is equal to 10 to the minus 5 times 10 to the minus 1 to the 1/2 is equal to 10 to the minus 3. Wow, I've got my H plus and my OH minus concentrations for a weak base and a weak acid. I'm going to convert these into pHs, by the way. If I want to convert this into the pH, let me do my pH calculation. pH equals 3. I'm going to do my pOH calculation. pOH equals 3. But then I'm going to take this one more step, and the pH plus the pOH has to equal 14. So since this is equal to 3 for the pOH, the pH must be equal to 11. And I'm feeling good about this. Here's a weak acid, which has a pH of 3, which is not really strong. It's in the middle there. And there is a pH, for the weak base, which is not really strong base, like 13 or 14. It's around pH 11. It fits with that idea I had where when I have that kind of table and I'm looking at it, the strongs are at pH 0 and 1, the strongs are at 13 and 14, and in the middle are my weak things, 3, 4, 5, 6, 7, 8, 9, 10 kinds of numbers for the pH. Look how simple these calculations were. Notice that I was able to do the weak acid concentration and the weak base concentration exactly the same way. What's funny is that for some reason the people who teach this in textbooks think that, oh my gosh, we've got to go and treat these as fundamentally different kinds of calculations. Well, they're not. They're exactly the same calculations. They use exactly the same kinds of equations. The only difference here is that I have to be able to switch back and forth between acid and base terrain if I'm going to get my pH calculations.